For this question, I'll be working through question 3 of the 2018 Mechanics exam level 1. Right, we said Marama is snow skiing and uses a ski toe to get to the top of the slope. The ski toe pulls Marama up the slope at 46.2 meters. The combined mass is 62 kilograms. Can calculate the work done for Marama to reach the top of the slope. Work is equal to the work is energy, which is equal to the potential energy gained. I'm going to write that here. Gained, which is equal to mass times gravity times height. And that is equal to 62 kilograms, times gravity for year 11s is 10 meters per second. And the height that she gains is 46.2 meters, and that is going to give me 28,644 joules. Really, I should round that up to 3 SF, but I'm only going to do that at the bottom. So I'm going to say down the bottom, I'm going to have the rounded answer, but you have to have the unrounded answer in there somewhere. And I've showed all my working because you've got to do that. So that is going to be 29,000 joules, because they've given you 2 SF, and that's the minimum amount. 3 there, but whatever. Right, it takes 525 seconds to pull Marama to the top of the slope. Calculate the power needed to get Marama to the for this question, ignore friction. Right, power is just equal to work divided by time. It's in your formula sheet. Right, so that is going to be equal to the work done is 29,000 joules. 29,000 joules divided by the time, 525, and that is going to give you 54.6 watts. God, this is stupid, isn't it? You got to get this question right to get this question right. I thought the NCEA had stopped doing that. No, it's been a while since I've ever done level 1, that's for sure. Right. Humans can, the maximum output wattage for a human is like 600 or 700 watts. FYI, Olympic cyclists, when they're doing like the Tour de France, they put out like, like 400 watts continuously. So that seems pretty legit. Although this is a machine doing that, so yeah. But you could probably walk up at the same speed. Right, Jake has a mass of 75 kilograms, is doing a jump. He has 3,200 joules of gravitational potential energy at the top of his flight. Calculate his downward vertical speed just before he lands, assuming energy is conserved. Right, so we got potential energy is going to be converted directly, because we've got energy is conserved, woohoo, just highlight that. It's going to be directly converted into kinetic energy. In other words, mass times gravity times height is going to be equal to half mass velocity squared. This threw me off a little bit because I'm used to doing, they've given you the gravitational potential energy. So this is going to be equal to 3,200 joules. Right. We're trying to find, what are we trying to find? The velocity. We're trying to find this velocity here. So we're going to have to undo this half. So on this side, so to undo a half, you times it by 2. So we're going to times this by, we're going to have, do it algebraically, mv squared equals, times both sides by 2. 2 times a half is just 1. And 1 times mv is just 1 times mv. You just leave out the 1. So it's 2 times 3,200 joules. Right, and now we're going to go v squared is equal to 2,000, just times this together, 6,400 joules. And it's mass times velocity on this side. So to undo it, you need to go the opposite of that, so it needs to be divided by mass. And now I'm almost there. Velocity is equal to the undo squared, we need to go square root 6,400. What's our mass? What is our mass? 75 kilograms. Stays up here. There we go. 70, 75. And you need to put brackets around this, because if you do this in your calculator, if it's like a graphics calculator, it'll do square root of 6,400 first, and then it won't do the 75, and then you'll give you a wrong answer. So make sure you put brackets around that when you do this in your calculator, and that'll spit out 9.24 meters. Boom. Look at that. Right. Explain why Jake's actual speed when he lands is slower than that is calculated in part I. So I'll pause, write it. Right, so I've said air resistance will cause energy loss to sound and heat. Also, air particles will gain kinetic energy when displaced. So I hate these questions when it comes to level 1 because it teaches a massive sort of misconception. If you're honing through the air, you're barely making any sound. Like, yeah, you make a little bit and you're making pathetic amounts, pathetic amounts of heat. Majority of the energy gets dissipated in the fact that when you've got air resistance, when you hit the air particle, say this is an air particle, your body moves, it hits that air particle, it's accelerated up and it's gained kinetic energy and it stole that energy from you. So that's really when like majority / 99% of all the energy goes. You're accelerating those air particles up. Yeah, they bounce off and shoot off to the side. That's a trade in energy. So you're trading your kinetic for their kinetic. That's really what happens with this sort of thing. But sure, you've got to put sound and heat because that's what all the mark schedules always have. But in reality, the air particles are gaining kinetic energy, and that's how it's actually slowing down. Right, last question. Right, Jake changes to... Oh, can we see that? No, we can't. Jake changes to his wide skis. The skis measure 10 centimeters in width compared to normal skis of 5 centimeters. Both skis are the same length. Explain why Jake does not sink into the snow when he uses his wide skis. Calculations are not required, so we're not going to do them. Right, so I'll pause, write it. Right, so I've said Jake's weight force is constant. The ski's surface area has increased, because it has, because you've gone from 5 centimeters wide to 10 centimeters wide, and I should put a comma here because it's not grammatically correct. From pressure equals force over area. If the area has increased and the force is constant, the pressure will decrease, so he won't sink as far down. That's why you wear, like, I don't know, snow boots as you're walking through snow.